Hi, welcome to my informal sort of presentation that I'm going to be doing. So I was considering for this doing just a normal regular report, just writing out some stuff, but I thought this particular creative that I've done, it's a simulation, it's interactive, it's not really that good for that sort of format, and you don't really want to be looking at a bunch of images, still images of stuff. So I'll just do a little bit of a talk about what I've changed since last time. I'll talk about, I'll do some slideshows. I'll just show exactly how my new code works. And last of all, I'll do a little bit of a demonstration as well, just to show you that it works. And just to let you know, all of this code is fully available on the link inside of the assignment document on my GitHub, and that's publicly available. So to just recap what I did last time, I created a 2D Turing machine simulator, and it is completely randomly generated. So each time you run it, a different Turing machine runs, and it's a complete transition function. So there is no halting for it. So essentially, it'll keep going forever unless it gets stuck in a loop. So I'll just show you real quick what we had previously. So this is my code for my Turing machine simulator. So previously, prior to assignment 2, we just had these 4 options. We had the number of states, which we could set our random generator to however many states we wanted, and then our number of machines and our grid size as well. So it's just those 4 things. Now we can see, I'll just put it on the default settings and we'll run it. We should see we get a little Turing machine. We can speed that up if we want to, and you can see that it starts making some patterns, right? So what we can do is we can also run multiple Turing machines as well. So this is inspired by the platypus game. We have multiple Turing machines running on the same tape, and they just alter the tape one at a time, so they take turns. So we can see if we run 10 in the same grid size, we'll see that they'll all do their own thing. And with 10 Turing machines, obviously it's going to be a lot more chaotic than with just one. And that's a general trend you can see. Also, we can turn off the heads. So if you don't like those little red pixels, you can just turn that off. That's great. So you might see that there's a bit of an issue with this, and that is obviously we can't save and we can't load. So if we find something really interesting, we can't keep that and we can't replay that at a later date. And since this was originally designed to be sort of a background screensaver sort of thing, that's kind of really important. So what I've gone and done this time is I've added loading and saving to files. You can also create your own Turing machines and import them instead of relying on the random generated ones. You can alter the colors just as a little bit of a novel thing. And also I've created what's called a termite to Turing machines converter. So I previously mentioned that we're going to be using termites, and I've made a termite to Turing machine converter. So let's have a look at what a termite is. So it's this little guy with a direction that he's facing, which can be one of 4 directions. He also has a brain, and that brain can have as many states as he wants. So in this instance, we've got a little guy with 2 states, those being fighting and eating. So here we can just demonstrate how exactly we put that into a Turing machine. Well, it's quite simple. In the rows, we have the 2 states. In the columns, we have the 4 facing directions. Now, to convert it from a Langton's ant, which has state and direction facing, to a Turing machine, which just has states, we get every combination of those 2. So as we can see, we have up and eating, right and eating, down and eating, left and eating, and so on with the fighting as well. So these 8 combinations indicate all of the states of our new Turing machine. Now, let's look at a very simple example, right? So it is in the fighting state, and it sees a tile that is white. So it can either turn to the right, turn 180 degrees, turn to the left, or not turn at all. So those are the 4 possibilities that it can do. Now, how do we determine which direction it's going to turn based on which way it's facing? Well, that is quite simple. So over here, we have our Langton's ant's brain. Now, this is for a Langton ant, and a Langton ant has one state that it's in. This is represented by this orange curly brace. So that is the state. We can see this black curly brace is if it reads black, and this white is if it reads white. This is what it will write. So if it's reading black, it'll write white. And if it's reading white, it'll write black. And it'll turn to the left, which is represented by this 8, if it reads this black. And it will turn to the right if it reads white. And of course, it'll stay in the same current state. So using this, we can see how we would be able to turn to face a different direction depending on the current direction. So we'll show here our transition function for this very simple termite. So for this one, we have the 4 states just being the directions it's facing, because obviously it doesn't have any actual states within the termite form itself. So it just has the direction that it's facing. And then it has the color that it's reading. Obviously it's going to switch the color when it's writing, and it'll also turn to the left. So if it's facing up, it'll turn left. If it's facing right, it'll turn up, and so on. And the opposite if it's reading white. And the very convenient thing about this is if we look at the transition, we can see the current state, then what it reads. This is what the next state will be, and this is what it writes. And we can see that this, which is the direction that it moves, is always the same as the next state that it's going to turn to. So after that really quick presentation, I'll just show you how exactly this works within the actual code. So we can see right here, this is a new file. This is our termite.py. We can specify right here, as I previously mentioned, that brain of that termite. So we can see right here, this is state 1, this is state 0. And these are the 2 possible colors within that state. So this is, in this instance, black and white that it's reading, black and white. So this is for a little termite that will create a Fibonacci ratio, a little golden ratio. So what we can see is if we press play on this, we should see that it will create a file called Fibonacci right over here. Perfect. And you can see that Fibonacci has 8 states, which indicates 2 times 4 because it has 4 directions it faces, and 2 states of the actual termite. So if we run this in simulator.py, we'll see we can just type Fibonacci, save that, and run. Make sure that we're reading from the file. And we should see it generate a nice little golden ratio if we speed this up a little bit. So we can see it's creating a golden ratio and it's expanding. Now, let's say that we are wanting to save. So I'll just show off that other feature as well. We have, for instance, a 2 machines on this grid. We're not loading from a file, we're just randomly generating them. And let's say that they have some interesting behavior. So, oh, look, they generate a very interesting pattern. So we want to save that. We can just hit S and it'll automatically save to a file. And that file is called save1. And we can see these are all the states and all the transitions. Wonderful. So we can just go in here and we can read save_1. Make sure we're reading from the file. And we should see the exact same behavior every time. So we can see it's doing all that, it forms the exact same pattern. And this is really good if you want to have a specific screensaver and you don't want to have to randomly generate each time and wait for a good looking one. So I hope you've enjoyed this presentation. I haven't managed to show everything, but I think I've covered most of the important stuff. And I'll just leave you with a few termites that I've converted, and I'll just play a little time lapse of a few of those.